So let's get some assumptions that we'll be using out of the way. The standard model of cosmology is known as the lambda CDM model. This is how I will be referring it throughout this talk for reasons that will become apparent soon. The lambda refers to the cosmological constant, otherwise known as Einstein's biggest blunder. He needed to add it to make the math of general relativity work, and then he took it out again. He died before we ever figured out what it actually represented. It was revived and reinterpreted as the energy density of space, or vacuum energy, that drives the expansion of the universe. But this was something that we only came to the conclusion about in the 90s. It is closely associated with dark energy and implies that the quantity of dark energy in the universe must and always has been constant. One problem: the discrepancy between theorized vacuum energy from quantum field theory and observed vacuum energy is drastic. I have been known to say what's an order of magnitude between friends, especially between astronomers, but to be honest, 120 orders of magnitude is taking the piss. The predicted value from quantum field theory is between 50 and 120 orders of magnitude greater than the observed value of the cosmological constant. The CDM part of lambda CDM refers to a hypothetical form of dark matter which has never been directly detected. We don't know what it is, just that it does exist. Despite all of this, we do have observational data that does support this model, and this takes us to part 2. One of the main predictions of the lambda CDM model is the existence of this. This is the cosmic microwave background. You likely saw this exact image, or a version of it, when it was unveiled by the Planck collaboration for the first time in 2013. It has been revised and updated since then. This is the most recent one from the 2018 paper. It may have been included in the 2021, I don't quite remember. This image is a map that shows the mass distribution in the observable universe. The bright red and yellow spots are where we find baryonic matter. Baryonic matter is anything that has mass, really. Photons, neutrons, all that stuff. The stuff that we are made of and the things that we interact with, or as Merlin would call it, an object. This lines up with other observations. And I'm going to go down a little bit of a rabbit hole and explain how this was formed, because I think it's really neat. At the time of blast scattering, which is the time when the photons that make up the CMBR were formed, before they travelled the 13.7 billion years to reach us, the entire universe consisted of a baryonic photon plasma. The thing is, about things with mass, they tend to clump together because of gravity, collapsing into regions where the density is higher than average. This led to acoustic oscillations in the plasma. Yes, exactly like sound waves, in a direct sense. They are compression waves or pressure waves in a gas. At this time, photons and baryons were strongly coupled, so they were stuck together. They couldn't get away from each other. The photons resisted this collapse, pushing the baryons outwards. The result is comparable to ringing, or oscillatory modes of compression and rarefaction in the gas because of the density fluctuations. The gas heated up as it was compressed and cooled as it expanded, and this is what creates the bright spots in the image. I said this is literally a heat map. Like, it literally is, and if this hadn't happened, we wouldn't exist. Because what this actually is measuring differences in temperature. Now, the parameters from these missions, looking at the early universe, studying the CMBR, are very much considered the gold standard of values of the fixed parameters that define the lambda CDM model. This is why the calculated Hubble constant, which is the rate of expansion of the universe, is considered the true value, the one that was derived from this data. It provides a high level of precision and accuracy to 4 significant figures even. It is 67.66 kilometers per second per megaparsec, with an error of plus or minus 0.40. That's very, very good. Because of these because these little regions here, physical position of galaxies and clusters in the observable universe that we can see, it is possible to work backwards from this to calculate the Hubble constant using these baryonic acoustic oscillations, which is what we call this phenomenon, to calculate distances. And this technique gives a broadly similar result of 68.2 plus or minus 0.81. These are called indirection measurements. They are the yardstick to which all other methods are compared. And the uncertainties between these two Experiments largely overlap, some variation is to be expected between techniques, and therefore there is no tension here. So where does the tension arise? To be clear, tension in this case isn't referring to a physical force. I had somebody say that when they read my dissertation. It is simply the name of this phenomenon in the literature, and I just wanted to clear that up. The tension, or conflict, one could say, appears the moment these values are compared to observational results. In the previous talk, I outlined the idea of spectroscopy, how it works, and why. And this is why I did that talk. I thought it would be interesting for you all to get some appreciation for the physics we needed to discover so we could start gathering this data, never mind doing anything with it. Also, quantum mechanics is cool, and the photoelectric effect is a decent introduction to the field. So, for direct measurements, let's start with supernovae, or one particular type of supernovae, called a type 1a supernovae. This is an artistic representation of a type 1 supernova. Well, it's not gone supernova yet, but it's a symbol system. These occur when one binary star in a star system goes supernova, when it can no longer maintain the pressure it formerly kept together due to reaching its critical mass. In binary star system, one star essentially feeds from the other, and it essentially rips matter away from its neighbour. Increased mass equals more fusion, equals running out of fusionable materials. Through successive nuclear fusion reactions, creating everything from helium to ion in terms of atomic mass. I shan't go into detail about how it all works. Stellar nuclear synthesis took me about 6 months to get my head around. I would be here all day if I tried. But eventually, they gain so much mass, they get so unstable that they can go bang. Well, it's not really an explosion in a traditional sense. It's not burning, and it doesn't, it does involve some oxygen, but that's not what we're talking about. It's more of a rapid expansion that happens over the course of a couple of seconds. It only takes about a quarter of a second for the core of a star to collapse, blink, and you would literally miss it. When this happens, they release a lot of energy in photon form. The peak luminosity is very predictable in this particular type of supernova because it's dependent on the critical mass of the star that is going bang. We can use the predicted luminosity and the observed brightness to figure out how far away they are. Intensity drops off following an inverse square law of proportionality of the form intensity is proportional to 1 over the distance squared. This is what has earned the name standard candles. They are used to create what is known as the cosmic distance ladder. There are other ways to calibrate the cosmic distance ladder, but they share a core principle. Look for astronomical phenomena that have a knowable luminosity, record the observed brightness, and use it to work out a lot of distances. Not to negate the work that goes into this area of research. It's very complicated to actually do this, and it takes a long time to process this data, but it's just not my thing in particular. These methods yield values of the Hubble constant between 69 and 74 kilometers per second per megaparsec. But we're going to get into my expertise now. Gravitational lensing. I put these up here partially to demonstrate how amazing JWST is. This is exactly the same image, different telescope. But I'm using these to mostly show you what we're talking about. So, you see here, where it looks like the light is bent. See how they're all warped? That's because they're not actually there. These are projections of galaxies that are behind this here. Gravitational lenses can be thought of somewhat like optical lenses. They just don't have a focal length, not really. In optical terms, it's the material's properties, thickness, and curvature that affect the light's path. In a gravitational lens, it's the presence of mass that bends the light's path. Now, to explain this and general relativity as a whole, very basic way, imagine a taut rubber sheet. Now put a bowling ball on the sheet. It rolls and it settles in the middle, depressing the plane, causing it to dip into the center. This is how mass interacts with space-time. Space-time, I'm going to put this in math language, space-time is the accepted mathematical model that combines all 3 physical dimensions and a single time dimension into one 4-dimensional manifold. That may sound like Greek, but don't worry. You don't need to understand all the math and the jargon if you just accept that it exists in all ways, that mathematical models exist, and it's been proven beyond a shadow of doubt. Just trust me, bro, it works. If you really want to get into the proofs, I cannot recommend Space-Time and Geometry, an introduction to general relativity by Sean Carroll, enough. You can try Wikipedia first, but it doesn't really do as good of a job as explaining from first principles, and it relies on already understanding tensors and having a high-level understanding of algebra. But I digress.
Photons emitted from astronomical sources, a star, galaxy, or quasar, are assumed to be radiated uniformly in all directions, like a point source emitter. When we think of light as a particle, we would accept light to travel in a straight line between the source and the observer. Light would travel in straight lines as space-time were entirely flat, but as I just explained, in local scales, it's not, because there's mass in the way. Overall, the universe is still said to be flat because in the grand scheme of things, everything's very far apart, so it cancels out as you zoom out and look at the universe as a whole. When we look at this image, what we are actually seeing is a projection of something that's behind this particular galaxy cluster. The formerly straight path of the photons that make up this projection have been bent, meaning that they have to travel further than they would if the lens was not there. I'm going to show you a diagram that I originally created for my dissertation that demonstrates the geometry at play here. It looks complicated, it's really not. We'll go through it step by step. So, here we have us. We are the observer. We are in the observation plane, point of reference, whatever you want to call it. L represents whatever makes up the lens. That can be anything from a planet or a star to a galaxy to a cluster of galaxies. There are varying ranges of lensing. I'm specifically dealing with strong gravitational lensing here, which is anything that's galaxy or bigger. And S is the source of whatever. S stands for the source of whatever is being imaged. From S, we have two solid black lines, representing two possible paths for the photons in this particular system. They start off with straight paths, and as they approach the gravitational field of the lens, they start to bend. The degree to which they bend is given the symbol xc. This is the impact parameter. The subscript denotes to which path you are talking about. Once it escapes the gravitational field of the lens, it carries on straight again. That's why the sources look like they're off to the side. I labelled the apparent positions of S1 and S2 to show where the images would appear to be in this system, where alpha and the alpha with the little hat correspond to the deflection angle and scale deflection angles. Theta is the observed angle. This is something that we can measure, and beta is what the observed angle would be if there were no lens in the way. Understanding the geometry of it all isn't too important unless you really want to study a lensing system, so to save you from the math, I won't go into it beyond this. At this point, it begs the question, why is this useful? Well, each of these images, of which there can be anywhere between 2 and what looks like a solid ring around the lens, have different path lengths, which means that there is a time delay between them. The number of projections, their magnifications and shearing depend on the distance and orientation of the source and the lens, as well as the properties of the lens itself. However, I promised you I would avoid the math, so once again, I am employing the trust me bro guarantee. Intuitively, that makes a certain amount of sense. A photon here, photon here has to travel a larger distance than a photon here. This leads to different values of redshift. That's where this gets more interesting and more useful. If we can break down the components of the time delay, we can extrapolate a lot of data. The first component is pretty simple. It's deflection. It's the geometric deflection I described just now. Calculate all of these distances along the bottom, measure the redshift, and you can calculate the geometric part very easily. The second component is where it gets tricky. We need to tackle the gravitational part of the time delay. This depends on the lensing potential of the galaxy or cluster that is forming the lens. This leads to some pretty nasty mathematical model, which we are avoiding right now. There are various assumptions that we can make about the composition of the lens and where the mass is located within the lens. To go beyond basic assumptions, we need to collect a lot of data about the properties of the lens so we can model the mass distribution, how the constituent parts of the lens are moving, and surface brightness to create statistical models. Using all of this observable data, it's a nightmare, and not all of this information has already been collected. This is why the current and future generations of ground and space telescopes are receiving beefer and more specialised equipment. We know what we need now, so now it's a case of getting it. Here is a graph. This is the pièce resistance of my dissertation. This compiles all of the strong gravitational lensing studies that have been done in the last 5 years. And the variation between the calculated results of the Hubble constant are wild. The blue band here represents the value from Planck and its associated uncertainties. The pink band is from 15 years of measurements of these standard candles that I was talking about earlier. This is the problem that I've been talking about. These measurements are wildly different from each other. Sure, some of it is uncertainties in individual models, but there are ways to mitigate these, and they have been. It can't be denied that there is room for improvement in lens modelling methods. There is an obvious need for more constraints on these mass models. But even when you generate an average of all of these sources, distance laser measurements, baryonic acoustic oscillations, time delay cosmography, which is just the overarching name of gravitational lensing research, cosmic clocks and light curve analysis, 2 areas that I don't really have the time or expertise to get into in this talk, the average is still 72.7, plus or minus 2.9. which is still in significant conflict with the CMBR measurements. So yeah, it is kind of all broken and we don't know why. It would be naive to assume that the flat lambda CDM model is perfect in every way, and a lot of researchers here have tried to remove any assumptions about the universe that we live in from the way that they have modelled things. We have different ones, so it's multiple lenses averaged over, making a statistical idea of the perfect gravitational lens. You have things where it's not flat, or it is flat. Like, we've thought of everything at this point. We tried to account for it. The Hubble tension has been a significant conundrum for many years, and it's been the focus of many researchers' careers. Numerous theoretical solutions have been suggested that attempt to reduce or remove the temperature between measurements already. I think there is a genuine possibility that with more data and the accompanying better constrained mass models, we could drastically reduce the uncertainties involved. Because after all, theoretically, a single perfectly modelled lens will give us all the answers that we're looking for. So, is it broken? Kinda. Science is always some degree of broken. We don't know everything, we don't know what we don't know, and we've only been working on this particular problem in this particular way for the last 30 years. It's just a really big thing not to know for sure, because so much of astronomy relies on this exact parameter. Yeah. Any questions?
If you go back to the slide where you see the lens,
Yeah.
are you able to point out like which galaxies are the same?
Yeah, so largely you look at this bit here, this bit here. Usually they are somewhat equal and opposite depending on the orientation of this lens. So typically what you're looking at is you're looking at one individual galaxy. It can be a bit difficult to differentiate between them. But basically every single one of these dashed lines is something being warped.
Yeah, and does that mean that the galaxy that's on the top right, that it's also somewhere on the bottom left?
Sometimes yes, sometimes no. It really depends on what you've got in front of you. Sometimes it can only be one. When we are looking at doing time delay cosmography, we are looking for ones that come in pairs at least. So if I go back here, that's my next slide. If we come back here, so some of these are, you'll see here, so I put the names of the research groups that are working on a particular thing. This is basically a guide as to which data sets have been combined. But you'll have some, so one of my favourites, do you have favourite research groups? I do. Holy Cow looks at individual lenses. They take one lens, they look at it, they study it, they break it down, they make a model. But TD Cosmo, which stands for time delay cosmography, and SLACS, which is a different thing, combines all of the lenses found by Holy Cow. So, yeah.
if you don't see the same galaxy twice at the other side of the lens.
It doesn't have a lot of value for this particular
Yeah,
thing.
okay.
Most are done, so that's why I used this diagram, because this is what I would call a doubly lensed quasar. So a quasar galaxy that's got a massive black hole in the middle. This is relatively common to happen where you get two images. It very much depends on the geometry of the system, where it is between the lens and the source. If you want to get into it deeper, I can send you a copy of my dissertation, because I explain all of that, essentially.
Is there a difficulty in the fact that the view that you see of the same galaxy, if I understand it correctly, it might be that the two views you see are of two different times in the history of that galaxy?
Not so much. So essentially, we are generally assuming that we are looking at light that was emitted at the same time, because it's continuous, essentially. It's released at the same time, but it doesn't get to us at the same time. Or it's had to go further to get to us. Everything that we're looking at is very far away, very far in the past. So I wouldn't say it's enough to be significant for that to be the case.
So even though it's traveling more distance at the lower thick line,
Yeah.
it's arriving at the
So
same
it arrives afterwards, that's the point. So we're working out the
time. So the
delay.
observer sees both.
Yeah, so you see both, but because because this line hasn't had to travel as far, it's less redshifted. And the amount that it is redshifted is a combination of the three different types of redshift that I explained.
So is this a very common phenomenon, the gravitational lenses?
It's not uncommon to see it. It's sometimes difficult to find ones which are suitable to be studied.
Yeah.
We obviously have a very biased sample right now. We find one, we look at it with multiple telescopes to gather more and more data. I think when I was doing my dissertation, I came across maybe 50 that had been in some way analysed. We are thinking with JWST and future telescopes that we will have hundreds more, if not thousands, enough to create a really robust statistical model.
The image you showed, the picture, the color picture.
That one? Or?
Is that one single shot, or is that a time?
Oh, so these are made up of multiple exposures. That's why, like, usually you'll look at something and it will take like a day or two of observations, because you look at it in different frequency bands and you build a composite image like these. Because like this was the first image released by JWST, that's why I included it, because it's essentially a picture of one of the lenses that has been studied the most from the Hubble Space Telescope, which is this one. So you can still see some of the lensing in here. Like, this was basically the confirmation that it happened. So for the first thing JWST to do was to look at exactly the same cluster. I thought was really poetic, and that's why I included it.
I think the same you should have with observation based on radio telescopes. Is it that, or is it more pronounced than?
What, sorry?
Observations with the radio telescopes.
Yeah.
Because this is optical.
Well, no, these aren't done in optical.
See?
These aren't these observations aren't taken in optical wavelengths.
In optical wavelength.
This is essentially, it's been adjusted for the redshift. So if we were there and we were looking at it, what would it actually look like? It's a lot of post-processing. Because everything really is just the peaks on the grass that...
Yeah. But the same lensing effect you should have with radio telescope, I presume.
Oh yeah, it happens with everything. But we are specifically, so with JWST it's focused on the infrared, because obviously stars let out heat, and we
Is
can
it
see that.
dependent? Is there a dependence on the frequency? I mean, infrared or visible light or a different behavior?
No, it happens. Photons are photons. The only thing that separates them is the amount of energy that they have. We are specifically looking at infrared, optical, UV because we know that that's what's being released. Because we know enough about stars and galaxies and how they work to know what phenomena we're looking at. We use different telescopes for different things. It just depends what we're looking at.
In this picture, is this gravitational lensing effect just caused by one lens, or do we have several lenses in this
So,
picture?
You talk about the lensing system because really what this is a cluster of galaxies that is causing this. It's got enough mass that it's bending space-time, enough that basically all of the stuff behind it is being bent by having to go around it. So this is a cluster of galaxies.
So what is your best guess to explain the tension or the conflict between is it just it's not constant or?
So that's a loaded question. I would direct you to my dissertation. But no. Having looked at it a lot, I think that there may actually be problems with the CMBR measurements. There are a lot of technical details behind it. If you have a quick Google and start going down the rabbit hole, you'll see all of the criticisms of it. I also do not think that the current model of the universe that we have is correct. A lot of people agree with me on that, but also it's the standard model of cosmology for a reason. I don't think it's perfect, and we've derived it from one type of observation from the indirect methods from the CMBR. And that's valuable, don't get me wrong, that is valuable, but I don't think that we should hold that as the pinnacle just because it's the most precise and the most accurate. Because when we look at things in our local universe, when we look at this lensing, when we look at the standard candles, it doesn't agree. And the whole point of the Hubble constant is that it's the rate of expansion of the universe right now. And it has changed throughout time. We know it's changed throughout time. But right now, they should all agree with each other, and they don't.
And on what do they disagree exactly?
As to what the speed is.
The speed.
Yeah.
So that 70 kilometers per second.
Yeah.
Yeah.
So obviously, yeah, this is very good. So everything, I mean everything, is moving apart at approximately 70 kilometers per second per megaparsec.
Mm-hmm.
So it compounds. Just think of it like a balloon inflating.
Mm-hmm.
It's inflating at a consistent rate. The Hubble constant, H0, is how fast it's expanding right now in this stage of the universe. We have a bunch of different ways of taking measurements, all of which seem to be about as accurate as each other. But they don't agree with each other, so why not? Only so much of it can be explained with uncertainty, statistical and systematic. We can combine them, we can reduce them, but it still doesn't explain away the tension.
This is a speed, but
Well, technically it's velocity because it has a
Sorry?
direction. It's velocity. It
velocity,
has a direction.
expansion velocity.
Recessional velocity is what we would call
Is
it.
it a constant?
It should be constant right now. It should be consistent. It should be the same everywhere because of the assumptions that we make about the universe.
But in time, is there a kind of acceleration? Or?
Oh, yeah, so this is one of the points. This is sort of actually how cosmology got started, theorizing different models of the universe, changing different parameters. Okay, well, what did this type of universe look like? What was this type of universe look like? A lot of them weren't particularly concerned as to whether it's what our universe looked like, just what one possibly could.
Isn't it because they don't know where exactly the pole is coming from?
Well, yeah, we also don't understand that either. I mean, we call it dark energy, but we don't know what dark energy is. call it the vacuum energy, what drives expansion, but we don't know what it is, and the way that we can explain it with quantum field theory gives us a value which is way bigger than the cosmological constant. But we know that general relativity works. We use general relativity every day. We know it works, so we know that the cosmological constant must be right, but it doesn't agree with anything else, so why not? We don't know.
Are there certain observations or new kind of detectors that would help in figuring out this issue? Or is it more that we need new analysis on the mathematics side or things like that?
I think the maths is covered. So the big thing with JWST, and we haven't actually got a value of H0 out of observations done with JWST yet, but this one here was used, and I try and remember the percentage off the top of my head. I put it in my dissertation about how much more accurate the data from this is than from this, because it involves detectors in the IR spectrum, so you're doing IR spectroscopy. It's basically collecting more and more data and then breaking it down into more and more things. So there are a lot of ways that affect the gravitational part of time dilation, which is very concerned with what is in the lens, how the mass is, how it's moving, how it's interacting with everything, because that affects where anything is at any given time, and that does change how it works. I will do a little aside though, because we are kind of computer scientists here. This, I genuinely think, is an excellent application of machine learning. People are already started doing it, making these models with no prior assumptions. I came across a paper whilst I was doing my dissertation, I think it was 1 Park, 2021, where they fed all of this data into a machine learning model, a Bayesian neural network, if you know anything about machine learning. I know too much, unfortunately. And they they picked a version, like a number for the Hubble constant. They didn't tell the algorithm what it was. They created a data set based around this, and it was able to figure it out to like within 0.5, which is about the same as the CMBR stuff. But we need to start feeding those things actual data, and we need to feed them a lot of data, because as you probably know, you need to train machine learning algorithms with a lot of data, and we frankly do not have enough lenses to do so. Not yet. But hopefully we will soon.
Not enough data.
Yeah, we don't have enough systems that we have
But then,
looked at.
what will it help? We won't be able to give any explanation why it comes to that value. It's just a blank box.
Well, so it's the way that we make the models. We pick out all of the different variables that contribute to it, because the Hubble constant is a calculated
Yes, if
value.
you have in your model 10 parameters or 20 parameters,
Yeah, you can
this
change how you
neural
can.
net has like
you-
5 billion parameters.
Yeah, but it's a very, very simple
Neural
one.
nets are not always explainable.
Yeah,
that's my
but,
point,
but that's
my
the whole
point.
that's the whole point. You set it at it. You don't give it any priors, and you see what it comes up with. And they did it, and they fabricated a number, and then it came to it with a reasonably high precision.
So then the conclusion is
Like-
that it finds a certain pattern.
It finds the pattern, which is what we're trying to do.
Yeah,
We're looking at the data, we're trying to find a pattern, so we can just write a computer algorithm that does it for us, and it seems like they're really good at it. And that was trained, I think, on like 500 simulated lenses. It took 10 minutes a piece to simulate these lenses. It takes us weeks, months, years. There are so many papers in the literature like, I have remodeled this lens, this is my value. I looked at this lens and this lens, I remodeled them, I made this assumption, this is my value. That's so much of what the literature about this is.
Is the model taking an assumption that the expansion is like in concentric spheres?
No,
Or
it's just,
maybe it's a lobe, and then depending on the position you are, you can see maybe the real velocity or relative velocity.
Well, it should be consistent at all times, so we're just assuming that it goes straight, that there isn't any variation of it, either in the large-scale universe or in our local universe, because it shouldn't be. Some people have suggested that in local areas of the universe, given things that are around us, that maybe it isn't the same everywhere. But if it's to agree with the model that we have, it should be the same everywhere. So if it's not the same everywhere, well, we need to look at the model that we're using. Because if that's the case, then something's gone wrong, and we just need to figure out what it is.
If I may add something, because it's related to my own talk, to answer your question about the thing that we get from the AI model, it's not explainable, but I would actually say that you have to be hesitant at thinking that mathematics explains things.
It doesn't.
Mathematics is something that we can use to predict certain things, but if you have a mathematical formula, for example, to predict what the shadow would be of an object depending on the sun, then if you just look at that formula and you state that formula as an explanation of what is happening, then you would think that you can increase the size of an object by increasing its shadow. And that's actually totally not the case. So it's not because we have a formula for something.
I'll rephrase.
It's
For
a
us
tool.
humans, explainable means that we as humans can understand it.
Well, we
That's what I
can
mean.
understand Lindsay models. Like, in reality, I'm not sort of pulling numbers out of my ass, but you can, I would say it's like less than 100 individual parameters that are being looked at, but you are looking at a lot of data points at the same time. That's why neural networks are good at it, because...
But I'll give another example. There was a few months ago a research paper that was using a neural net to predict whether the iris was not RGB, was not visible spectrum, was some other spectrum. So of a person,
Yeah.
the iris of a person, to be able to predict whether it was a man or a woman.
Okay.
And so the current status of science is there's no difference
Yeah.
for men and women. This neural net can predict gender with 80% accuracy. And so then the only conclusion is there must be some pattern.
Yeah, there must be more to it that we
But
don't
that's
understand.
where it stops, huh?
Well, you've got to be careful about overfitting your data there. I don't know anything about the model that they created or how they trained it.
Could very well be that the pictures that it's trained on include like the
Yeah,
brow,
that's also.
and then
Yeah.
based on whether or not the brow is it's possible.
Yeah, like, it very much depends on how it was trained. Like,
It also depends on which data is used
yeah,
and which part. Like a model, a trained model, can predict, can have, if it says something about the population,
yeah.
or who can be president or so, it can, depending on the data, it can act very biased and like racist.
Yeah, I know. We implement our biases into everything that we do.
So it can give you a totally wrong impression.
This is why I like math. And I like making mathematical models for things, because math is not really that biased. It can't be, because if it was, then your predictions would be wrong. And this is slightly what we're getting at right now. Because we want to make everything as simple as possible, because Occam's razor and all that, as simple as possible. Model is the most likely. So we have tried to make it very simple. We've tried to integrate general relativity into the standard model of physics, and it just doesn't work. And whoever does that will probably be the first person to win multiple Nobel Prizes in a row for the same work. I don't think that's allowed under Nobel rules, but I feel like if somebody can unify general relativity and the standard model of particle physics, they would be like a god to me. Okay, let's put it that way. Any other questions? Lest we devolve into machine learning speak for another half an hour. Alice?
Yeah. So, you mentioned that the Hubble constant has changed over time.
Yes.
Do you know, is there a current rate of change to that?
So right now, outside of the initial stages of the Big Bang, we largely think it's been the same. this whole
So
time.
what I want to know is how that compares to the time scale of what's in this picture.
Oh, in this picture,
So I'm assuming the foreground object is being assumed to be close enough that it's still at the same rate.
Yeah,
So
but you have to go really far back in the universe's history to look at the variation.
isn't the background image in here is on the scale of that far away?
No.
Okay.
Not even close.
Okay.
Our observable universe is how much light has managed to come to us in the time that the universe has existed. The universe as a whole is thought to be somewhere in the region of, I think, 42 billion light years.
James Webb Telescope, James Webb Space Telescope advertised as being able to look back to the Big Bang, or very close to the Big Bang.
Well, that's what we're doing. We're looking closer and closer to the Big Bang, but we are still limited by the amount of time that light has had to get to us, because that's a very large number.
So you're saying
I could talk for 10 seconds.
So you're saying that the Hubble constant has been approximately constant since the universe
very
became
early on.
translucent?
Yeah, since very early on.
Okay.
Alex?
I have a question, maybe a more general question, but
Yeah.
when you talk to particle physicists
Yeah.
about the current state of the field and what is being, what governments are pouring money into,
Yeah.
things like the Large Hadron Collider,
Yeah.
there's a lot of skepticism about whether or not this type of work will actually give any results that are usable.
Oh yeah. This isn't about being usable. This is about figuring
Yeah,
out.
no, I don't mean usable in terms of like practical value for society,
Yeah.
but there it's even usable as in even the scientists.
Yeah.
Some of the scientists are very skeptical that they will learn anything new just
Yeah,
by having a bigger
Yeah.
collider.
I don't think it's fair to say I have a dim view of particle physicists. I certainly don't. I respect them. I somewhat struggled with the nuclear side of physics, all of the equations and balancing everything and all of the different types of particles. That went a bit over my head. I was more interested in the space stuff. But it's just smashing things together and seeing what comes out. And I mean, we discovered the Higgs boson, didn't we? We didn't think we'd do that, but we did. You don't know until you try.
Yeah,
And that's the thing with CERN. I love it because it's like a gamble of humanity, but like, let's smash things together and see what happens, okay?
I'm wondering whether or not there's the same kind of criticism for cosmology, like before the James Webb Telescope was launched, did people think like, oh, we're not going to learn anything new from this larger telescope?
There are obviously some people who think it's a waste of time. Hell, I used to have a friend who thought exploring space at all was a complete waste of time. Surprise, surprise, she's no longer a friend. I hope she's not watching this. I post a VOD on Facebook later.
You get pretty pictures though.
You get pretty pictures. You get a lot of pretty pictures, indeed. Yes.
Going back to your first slide, I think, the background noise universe. Yes, that one.
Yeah.
It came to my attention that I see on the scale 300 microkelvin.
Yeah.
And here, there, minus 300.
Yeah.
What does it mean? Because you have 0 Kelvin
Variation.
variation.
Yeah.
That is a very, very, very tiny amount, I think.
Yes. It is.
It comes to my mind that it could be also a systematic error of the sensors.
No. This is basically looking at the intensity of This is essentially looking at the intensity of microwave radiation. We can measure that incredibly precisely. That's why the CMBR stuff is really well respected, because it's very precise and it's very accurate. We are just genuinely talking about tiny fluctuations, because when you step out, like, this is the entire observable universe. This is all of the radiation that's been able to come to us since the Big Bang. There is way more universe beyond this, but we can't see it because it's not hard long enough to get to us, because light still has a speed, and in the grand scheme of things, it's quite low. So, these, like, they represent galaxies, stars. They're hot. Like, they have really high temperature, but the variation is very small because they really are very far apart. Not to put too fine a point on it, but there's a lot of space in space.
What are the lines on the?
If I remember correctly, it's the galactic plane that we're looking through, I think.
I believe it's the Milky Way that's
Yeah,
been
basically you sort of subtract it because
gas will come back around.
I wouldn't like to have a sandwich with so much space in between.
God that we're on Earth and everything is us sized.
Right. The microkelvin variation that's directly related to a frequency difference in receiving, right?
Right. What's your understanding of temperature? Average kinetic energy.
Yeah.
Yeah, basically. Just think of it in.
But I mean, the measurements.
It's a proxy for the amount of energy that photons have.
But the thing that's actually being measured is just a microwave frequency, right?
Yeah. Well, intensity, yes.
Okay.
Because microwaves have a set frequency. So they exist within a frequency range. This is intensity, like how many photons are we getting in this spot versus this spot versus this spot.
How does it compare to the way we measure stars? Because we measure them also by the amount of Kelvin.
Yeah.
How does it compare to?
Right.
Because stars we say, okay, 3,000 Kelvin or so.
Yeah. So that's the
hotter or the colder or whatever.
yeah. So we use temperature sort of as a proxy for energy there. That is the temperature of the black body radiation. So when we say that a star is like 8,000 degrees Kelvin, that is the temperature of the radiation. It's a whole thing. Have a look into stellar nuclear synthesis if you want to understand how it all works. It's very dependent on the nuclear reactions that are happening in the star, its size, all of that wonderful nuclear physics. Anything else? I'm cautious about going over too much because they need to do an outro talk and everybody needs to help us move. That's okay? Good chance? Yeah?